today's session. Our first speaker is Si Li from the Tsinghua University, and he will talk about elliptic chiral homology and quantum master equation. So thanks, you can start.
Okay, maybe let me share the screen first. Okay, can you see the screen or?
Yes.
Can you see this?
Yes, we can.
Okay,
yeah.
great. Okay, great. Okay, thanks very much for the introduction, and thanks for the introduction. Yeah, I'll be talking about some recent works related to two-dimensional chiral conformal field theory and quantum field theory as well. So it's about elliptic chiral homology and something related to the quantum mass equation in B-way quantization. So here's the motivation. We know in this story of deformation quantization, we have a deformation quantized algebra on, say, on symplectic manifold, or it can be on Poisson manifold in general, as described by Kontsevich. And there, on this space, there's a unique linear map on this quantized algebra, satisfying a normalization condition and the trace property. So the trace F star G, the same thing as trace G star F. So it's like a trace. Then if you compute trace 1, you find this expression like aerogenous and with some kind of classes. And this is the Algebraic Index theorem, which was first formulated by philosopher Nasican as the Algebraic analog of Atiyah-Singer index theorem. And now if you replace the circle by an elliptic curve, and you work with like two-dimensional sigma model, and as explained by Witten, you could find some index of Dirac operators on loop space. So although the analysis of these Dirac operators, the index of the Dirac operator is not known yet, it's infinite-dimensional geometry, but still we would like to have some 2D chiral analog of algebraic index, and that's one of the main purpose of this talk. And so basically, we are mainly interested in sigma models about the mapping space from a worksheet sigma to a target X. And we're going to do quantization in the framework of B-way quantization. So the output is something like on the worksheet, we have some kind of algebraic structures living on sigma. It's given by some factorization algebra. I'll explain a little bit more later. And such algebraic structure will glue on the target in some kind of low energy effective theory. And they can be glued in terms of Gelfand-Gastin formal geometry. And in working with this setup, you will find interesting index theorems, like both the algebraic index and also the chiral index. And the other motivation comes from mirror symmetry. And I guess a lot of people know mirror symmetry, but roughly speaking, it's about duality between like a symplectic geometry, which is called A model, and a complex geometry, which is called a B model. So they all come from an infinite-dimensional integral, like integrations on the mapping space, but with different theory. So in the A model, like this infinite-dimensional path integral, it's hard to make it rigorous, but it's going to be localized formally to holomorphic maps. And this is mathematically well defined and give rise to like a Gromov-Witten theory. Now, formally, if you do Fourier transform, and this guy becomes another model, which is called a B model. And this path integral is still EO-defined, but if you work formally, you find it's going to be localized to constant map, but in a very subtle way. So intuitively, we would like to count constant surface on the target, in particular on Calabi-Yau. And no matter what, if you work with, like, say, counting spheres, rational curves, you're going to find like a variation of Hoche structures. So this B model can be viewed as a suitable way to count constant surface and you get this Hoche theory and also its quantization. And that's why it's interesting. And this also will fit into our discussion later. That's also one of actually the original purpose of this work. And there are many interesting models like fitting into this setup that I will be describing. Like for the one-dimensional case, probably is topological quantum mechanics give rise to the algebraic index. And our main purpose in this talk is going to be some kind of chiral deformation of conformal field theory. And many others like topological or chiral, like for example, this Kontsevich and Catano Felder's Poisson sigma model, and one of our main examples and many others. So I just list a few of them. Okay. Now, I'm going to be working with like a BV quantization. So let me say a few words about this BV. And this Battalion-Mikovitsky BV algebra basically is a pair, the following information. First, A is the graded, Z-graded, or sometimes people work with Z2 graded, commutative associative unitary algebra. And this delta is a linear operator of degree 1, which squares 0. But this guy is not a differential, it's not a derivation. And the failure of this one being a derivation defines the so-called BV bracket. So in terms of formula, it's given by this guy. And it satisfies some kind of graded version of Leibniz rule, which roughly says that this one delta operator is of degree 2, something like that. But this is roughly speaking what a BV operator or BV algebra is. And actually, this BV structure originally come from the quantization of gauge theory. So it's the most general framework to quantize series with like a big or arbitrary gauge symmetries. Now, one of the main important structure in this BV quantization is so-called quantum mass equation. But I'm going to express this quantum mass equation in a way, probably it's not that familiar to people, but this is going to be equivalent. So suppose I have a train complex over this power series in H bar. So it's H bar linear, train complex. And so it's a quantum in some sense. And then this kind of H bar linear map is related to the correlation functions in some way. This map is the target of this map is actually a BV algebra. A is a BV algebra, so it carries a BV operator. This guy is said to satisfy quantum mass equation if the following equation holds. So roughly speaking, this equation says like this correlation intertrains the differential D on the complex with H bar delta. Delta is BV operator on the right. So it basically says like this train map. And for example, I mean, in the simplest case, like if you work with like a trivial train complex, like the differential is 0, and if you work with like a element in this BV algebra with H bar dependence as a quantum corrections, then you define a map like multiplied by e to the I over H bar this expression, then this map satisfies the quantum mass equation if and only if this I expression satisfy this equation. This equation is more familiar to people, like this is a form of the quantum mass equation. So this is a one special case. But this train map is going to be quite in general and fit into our discussion for some different models of quantum field theory. Now, let me say a few words about the output of a BV quantization in quantum field theory. So if you quantize this model in this BV setup, you're going to find the following data. First, you're going to find a so-called factorization algebra. It's an algebra of the observables, like describing how like points collide and operators collide and the non-local operators and so on, all these structures. And the precise construction, I mean, in this BV setup in perturbative region is described by Castello and Gilliam. Rigorously. And if you have these observables or this kind of operator algebras, you can cook up some train complex. And this depends on the model, depends on dimension, and depends on the model. I will give you some examples later. Some kind of train complex related to the algebraic structure. And then you will have a BV algebra. And this BV algebra comes from the so-called zero modes of the theory. So related to the cohomology. And also on this BV algebra, you're gonna find a so-called BV map, which intertwines the BV homology. That's also a very general structure you're gonna find. So this BV integration depends on the choice of the so-called gauge fixing condition. But anyway, and then you're gonna find so-called correlation functions from this chain complex of the observables to this BV algebra. So this is zero modes. And this map is basically correlation functions, but this map somehow intertwines the UV theory with the IR theory, for example. So integrating out like non-zero modes, and you end up with zero modes. That's roughly speaking what it means in quantum field theory. And this map satisfies the quantum mass equation. So it's basically a chain map, intertwines the differential in this chain complex with the BV operator. And this is going to be also a general structure. I will say a few words about examples. Then eventually you're going to find one interesting thing is the index of the partition function. And this index is going to be the index related to the algebraic index and the Chiral index. So that's going to be the general structure. And but let me give you one example. This example is one-dimensional topological quantum mechanics. So it describes like a circle mapped to some kind of target. And simplicity target, for example, local operators are given by Y algebras, and the chain complex is given by the Hochschild chain complex if you put a lot of like operators on a circle. And the BV algebra is given by differential forms, and the BV operator is the lead derivative with respect to the Poisson tensor. I can glue such a thing on a target symplectic manifold. You're gonna find the Y algebra, so-called bundle of Y algebras, and this bundle carries a flat connection, which is called a Fadasov connection. Yeah, as described by Fadasov. And it turns out like this Fadasov connection is the same thing, the geometric interpretation of the quantum mass equation, as we showed in the previous work. Then if you compute the one-dimensional correlation functions, and then you will find a trace map on this deformation quantized algebra leading to the algebraic index. And this map explicitly is described originally by Fajan, Felder, and Schrockit. And you can also find this map in the field theory interpretation in our work later on. So that's the one example. But my main purpose here is to describe the two-dimensional version, like Caio version, and the Caio analog of index theory. Now, I'll be working with vertex operator algebras. Yeah, I guess people are familiar with these notions, but again, let me just remind you. So this vertex algebra is very different. It's a little bit different. It's like 2D analog of associative algebra. And like it carries many structures like a state field correspondence. So you have an element, you can get an operator acting on itself with a dependence on a complex variable z. And you have the operator product expansion. So when points collide, it depends on the location, like holomorphically. And so you have a power series expansion. And this is basically the 2D analog of associative product, if you like. And for example, like many free CFTs give rise to such examples, like a Caio bosons, like a beta gamma system, BC system, and so on. So here's the table to compare this to like one-dimensional case. Like operators live in the one-dimensional case, for example, circle. They can multiply from the left and from the right, you get an associative product. In 2D case, like on the surface, you can have OPEs depending holomorphically on the location. That's the Caio version. And that's where we find this kind of Caio vertex operator algebra. Now, and if you work with like a Caio sigma model, again, similar to this topological quantum mechanics, and this model will produce a bundle of Caio vertex operator algebras living on a target. So this is the glue of the algebraic structures living on the worksheet. And you can view this one as the Caio analog of wire bundle. And for example, one famous example in the literature is the Caio drum complex. That's one case. Again, you can quantize this model. I mean, if you study this quantization precisely, this is a full solution. I mean, this is a theorem I proved a few years ago. It's like this. If you quantize this 2D Caio model as a Caio deformation, for example, as a Caio deformation of free CFTs, and in the BV setup, in the BV quantization, so this BV quantum mass equation, the solution of the quantization, is equivalent geometrically to solve a flat connection on the vertex algebra bundle of the following form. Like this connection is like takes the form like D plus like a commutator, like operators coming from an element. This element is like a one form value in the vertex algebra bundle, and this modes describe the corresponding Caio vertex operator acting on the algebra like fiberwise. And this square 0 is equivalent to quantum mass equation. So you can see like this is the Caio analog of Fadosov connection, and they have the same interpretation geometrically. So they are all coming from like a quantum mass equation. Like again, I mentioned this quantization is formulated in this BB form, like a BB setup. And also, if you work with locally, I mean, this is also give rise to like a BRT reduction of Caio models. And this is a very powerful applications to some other stuff like W algebras and so on. For example, if you have some kind of Caio algebras coming from BRT reduction, and this gives rise to actually a physical model realizing this reduction, the local operators of the reduction. So this one way to look at this theorem. But this completely describes this quantization of this 2D Caio model. And this theorem is proved like using some kind of effective renormalization theory. Now I come to the main part of the talk. This is like elliptic Chiral homology. Let me say a few words about its history. So like in 1994, Yongchang Zhu, he studied the space of so-called genus 1 conformal block, which now is the same thing as like zeroth elliptic Chiral homology. And he established basically the modular invariance for a certain class of like vertex operator algebras. And later on, like we know, like this Bayesian dream field, they have a big framework and define the Caio homology for general algebraic curves using the Chevalier cluster complex and also a categorical approach. And recently, actually, Akron and Holuani, they describe a very explicit complex leading to the few terms of this Caio homology, the leading terms. I will say a few words about their construction, which going to be quite related to our discussion. So roughly speaking, this Caio homology, again, describe the Caio differential in this Caio complex, describe like how points collide, like in two-dimensional surface. We know like in one-dimensional case, we have the Hochschild complex and the Hochschild differential. If you think about Hochschild differential as defining something on the circle, then this Hochschild differential describe like a colliding of like a pairwise points, for example, in neighbor points. Then you can do something very similar in two-dimensional case. If you work with like a Caio algebras or vertex operator algebras, and the OPEs of this guy living on this surface give rise to a differential that's called a Caio differential. Now, let me be a little bit precise for a few terms. I'm going to describe in this elliptic case, elliptic Caio homology. So suppose I have a elliptic curve realized as a quotient. So for each n, let me denote Fm by to be the ring of meromorphic functions on the product of elliptic curves. But it may have possible poles along diagonals. So that describe actually very general stuff coming from correlation functions of local operators. Then they give rise to give explicit expression of leading terms of this elliptic Caio complex model on the following guy. Like this is very similar to Hochschild complex. You have like n copies of the vertex operator algebra tensor with this kind of functions on the product of elliptic curves, modeled by some relations related to like some kind of global symmetries and so on. And for example, this complex, say a few terms of the complex, like say 0, C1, C2 with differential, like C0 is like one copy of this vertex algebra with F1, C1 is like two copies, and C2 is three copies, and so on. So what the differential look like? Suppose you have elements from C1, and suppose I have holomorphic functions Merrill functions. Let me decompose this one as a power series in such a way. Then the D1 look like this. Suppose you have two like vertex operators and one functions, and it turns out this function can be written in such a way. Then you basically compute the OPE and compute the residue weighted by this function, and you get the element of the vertex operator algebra. And that's the target of the D1. This is the value of the D1, the differential. Similarly, if you describe D2, so you start with element of C2, for example, like three elements of this vertex operator, and with a function in three variables, like the functions on the product of three, the curve. Then the differential look like you look at the pairwise OPEs and then compute residues. So like the OP of B with C and weighted by the function, and AC and B and AB and so on. So whenever you compute OPEs, you basically compute residues weighted with respect to the following of the function, and you basically do Taylor series expansions to compute the residue. And that's roughly speaking how this differential look like. So you see, like this is basically the analog of Causal differential, but you have this new information from the OPE with the holomorphic geometry coming in. Then this identity, like d squared equals 0, follows from the virtual identity, and you can denote homology, which turns out to be the same as the Kaio homology of the Elliptic Kaio homology. Then our goal here is to understand index theorem in this setup. So I mentioned before, but here, like we're gonna do B-weight quantization and find a so-called Caio trace map. This is a Caio analog of the trace map in algebraic index theorem from this Caio homology to some numbers, the trace. And that's gonna be leading to the Caio analog of algebraic index theory. So to describe this map, I need the notion of Caio conformal block, which basically is a collection of the correlation functions for local operators. So you have some kind of local operators, you put them on the surface, you compute correlation functions, give rise to some kind of meromorphic functions on the product. But depending on the operator, they could have very high. Could be very singular along poles. So it could be very high poles along all the possible diagonals. So when points collide, they can be singular. But that's what they look like. And similar to the case of topological quantum mechanics, this 2D analog, Caio analog of this solution of the quantum mass equation, it turns out to be expressed in terms of these integrals of this correlation functions on the product of on the Riemann surface on the elliptic curve. And that's something we need to figure out. But actually, we know this correlation function is very singular. It's very singular along the diagonals. And this is very different from this situation in topological field theory. We know in topological field theory, this guy is also singular, but if you integrate, they're gonna be convergent because this guy can be extended to a compactified space of the configuration space, and with corners, for example. But in this case, the Caio case, it's gonna be very singular, and there's no way to extend it to the compactification. So it cannot be convergent like naively. But luckily, there's a way to resolve this issue. Actually, we find an intrinsic way to renormalize such integral. We call this one regularized integral. This is a joint work with my colleague Jejo last year. So I use this notion like the integral with a bar. And if you do this one, and you find the precise meaning of this 2D correlators, this analog of trace of like a 60 orders of these operators. It turns out like this regularized integral of the conformal block exhibits all the required properties, so like something like a holomorphic normal equations, a contact equations, and so on. It's a very simple but very useful notion. So then we have the main theorem here. So I describe the theorem in terms of in terms of example of a combination of beta gamma BC system, but it's also true for Chiral bosons and so on. So first, we can construct a map. This map basically is given by like using Feynman diagrams from like n copies of like a vertex operator algebras with like a meromorph function on the nth copy of the elliptic curve to some kind of differential forms on the product, but with poles along diagonals valued in the BV algebra. That's very easy to describe just in terms of Feynman diagrams. But this is basically this is the integrand of the Feynman diagram. Then if you want to integrate, you need to use the regularized integral as I described to get this map valued in the BV algebra. So you integrate out the stuff on the elliptic curve. You end up with element in the BV algebra. It turns out that the Feynman diagrams combined with the regularized integral give rise to an element, a map solving quantum mass equation. So this map, this combination intertrains the Chiral differential with the BV operator. So this completely describes the situation for the quantization of 2D Caio models, like the algebras of the local operators. And with this one, so basically this is the answer to the first problem, like this for the Caio model. But what about a Chiral index? So with this one, you can describe the Chiral index in the following way. You want to describe the partition function of this Chiral deformations by some kind of Chiral Lagrangians, like say L. The Chiral Lagrangian is like it only involves the say some holomorphic derivatives. And you can also treat this one as an element of the Chiral vertex operator algebra. Then if you quantize the theory on elliptic curve, then if you can compute the 2D correlations, this is description like it's a combination of the Feynman diagrams with the regularized integral. So the left-hand side. But this guy is going to be something which has modular property, but it has mild dependence on the mild anti-holomorphic dependence on tau. So it's so-called almost holomorphic modular form. So you can set there's a canonical way to set so-called tau bar goes to infinity to remove the tau bar dependence. You get something holomorphic. And then this in the limit you find the Q trace, the usual Q trace described like in the most physics literatures, like a Q trace of the 2D model. So the Q trace comes from basically a way to realize this elliptic curve as some kind of quantum mechanical models if you choose A cycle and B cycles. That come from this tau bar goes to infinite limit. So you lose modularity, but you gain holomorphicity. And then somehow you can view this one as a Chiral algebraic analog on the loop space. And the reason such a thing works is precisely because the regularized integral has a very nice property. So if you start with a function, a meromorph function on the product of the curves, and you can do this regularized integral as I described. But on the other hand, because this is meromorphic, you can integrate this guy on like A cycles. If you choose n disjunct A cycles, you can integrate them, and this doesn't depend on the deformation of the A cycle locally. Then if you average the order of A cycle integral, it turns out that this one is the same thing as the tau bar infinity of the regularized integral. And this formula basically links the 2D index with the 1D Q trace. And this explains why such a theorem would hold. And but this formula also is proved in my work with Chiral. So as a summary, I have this table. So in the one-dimensional case, one-dimensional topology quantum mechanics, we have this associative algebra. Then we have the Chiral homology, Chiral complex. The quantum mass equation intertrains the Chiral differential with BV. And these correlation functions can be realized in terms of integrations on the compactified space of the configuration space. Then you find the algebra index. In the 2D case, you have vertex operator algebra. Then you have the Chiral homology. And this quantum mass equation is going to be intertraining this Chiral differential with the BV operator. And this 2D trace map is going to be described in terms of the regularized integral. And then you're going to find this elliptic Chiral index theory. And this is joint work in progress with my student Zhenping Gui. And that's all I want to explain. Thank you very much.
Okay, so are there questions from the audience? Yes, Giovanni?
Yes, hi, thank you for your talk. So this beta, gamma, and BC system originates in perturbative string theory, right? But the difference, if I understand correctly, is that there you have both the left movers and the right movers, the anti-holomorphic. Can you,
yes.
But also, can you also get solutions of the quantum master equations in that setting? Or?
Here I only described the chiral part, so it's the only part, half, like let's say left. Right. I don't include the right part. Actually, if you include both, I'm gonna find this logarithmic divergence. And the theory, the chiral part is completely UV finite. But if I include both, I will have this logarithmic divergence in general. And in such a case, I need to do a little bit more work in normalization. But I don't have the like a complete theory yet.
Thank you.
Yeah, thank you.
Okay. Are more questions from the audience? Yes? Yes?
Can you say a little bit what this regularized integral really is? How do you define it? What do you do to make it regular?
Yes. Actually, this is defined in the following way. So if you start with differential form, let me say how to integrate a form on a Riemann surface with poles along some points. So you have a differential form which has poles along many points on the Riemann surface. There is two forms, and what you do is the following: you can decompose this form as a sum of two terms. The first term is like a differential form with only logarithmic poles along this poles, logarithmic poles, and with another term which is holomorphic with the holomorphic theorem applied to some other terms. It collects all the singular terms, but the other term is the holomorphic D exact. So what you do is like you throw away this holomorphic D part, you integrate out this logarithmic part, then it's going to be convergent because log terms can be integrated. But if you have a surface with boundary, then you have to put this holomorphic D exact part on the boundary to integrate. Then it's also well defined. Maybe I can share another slide. I don't include this definition here, but hold on. I can find a better explanation in, hold on. Just a few minutes. Actually, this is an interesting point. Can I share another slide or?
So not from
maybe
this slide.
I want to share another slide. Yes. Yes. Okay. Can you see my slides?
Yes.
Yeah, this is how this is defined. So suppose you have two forms with some poles along some divisors. Yeah, I want to integrate this guy on the Riemann surface. They decompose these two forms as one part, which is two forms with at most logarithmic. The other part is holomorphic D exact. Then you define your regularized integral in the following way. So you integrate alpha, which can be integrated because it is log, and with integrate beta on the boundary. And you can show this one doesn't depend on the choice of the decomposition, and it's intrinsic and is invariant under conformal transformations. And that's, roughly speaking, how it works. In general, if you integrate on the product of curves, then you just integrate like factor by factor. It can show it doesn't depend on the order. And it's other nice property of the regularized integral. Hopefully this
Yeah, thank you. Thank you.
Okay, I think we should move on. There was a question from an online question, but okay, you already answered that. And so we can thank C again. Okay. And we move on to the next speaker. Okay, so here. So our next speaker is Nicola Pinamonti from the University of Genoa, and he'll talk about equilibrium states for interacting quantum field theory. Nicola there. Okay, so you can start. You can start.
Okay. Thank you very much, Alberto, for the presentation, and thank you very much for the opportunity you are giving to me to present this research at the ICMP 2021. So, the original part of the things I will present are obtained in collaboration with some people, and I want to mention here Nicolò Drago of the University of Trento, Federico Faldino, and João Braga Vasconcelos, students at the University of Genova. And then there is Romeo Burnetti from the University of Trento and Klaus Friedenagel from the University of Hamburg. And so in this talk, I would like to present the construction, a recent construction about states of equilibrium for interacting quantum field theory. But let's start with a bit of history. So let's start from very simple and known things. And let's remember how the observables are described in quantum theory. Usually observables form a sister algebra. And actually in this sister algebra, all the information about the commutation relation and these things are stored inside of the product in this algebra. And then the other ingredient you need to have in order to introduce what is an equilibrium state is a time evolution, which describes the dynamics of your system. And usually the time evolution is described by a one-parameter group of star automorphisms of your sister algebra into yourself. And then when you have these two things, you are what is known as a C-star dynamical system. And usually a state is nothing but a linear functional which is positive and normalized over this sister algebra. And among all possible states, we are here interested in finding the states which describe equilibrium. So usually equilibrium states are characterized by the celebrated KMS condition, Kubo-Martin-Schwinger condition. And this is a condition which essentially says that if you build a function like this one here, using your time evolution, your star automorphism, or describing the dynamics, you can extend this function for every couple of elements in your algebra as to an analytic function when the imaginary part of time is inside of some strip. And then when you analyze the boundary value of this function, you realize that they are connected essentially in this way. And this parameter beta, which appears in this definition, is the inverse temperature. And so why this condition is important? Well, first of all, in cases where you have an Hamiltonian at disposal, when you represent your algebra inside of some Hilbert space, and if you have an Hamiltonian, which is a self-adjoint operator inside of your representation, whenever the exponential of this Hamiltonian is trace class, then you can build a Gibbs state, the celebrated Gibbs state, which are assumed to be equilibrium state of your system. And actually, you can immediately recognize that Gibbs state are actually KMS state, which satisfies this KMS condition. But here there is a bit more, because the KMS condition can be used also for cases where this density matrix rho here is not well defined. And so, for example, for systems which are infinitely extended. And furthermore, in the past, there was a lot of work, and it was also possible to prove that this KMS state satisfying the KMS condition are quite nice things. They are, for example, stable under perturbation of the dynamics. let's see a little bit in more detail what I have in mind here, and in particular consider somehow a perturbation of your Hamiltonian, here denoted by this P, and then you can build the perturbed dynamics out of this perturbation Hamiltonian in this way. And the free dynamics is intertwined into the it's transformed into the perturbed dynamics with this adjoint action of this unitary object. And this unitary object here, its derivative at time 0 is nothing but up to an I is nothing but the perturbation Hamiltonian, and this U of t satisfies this cocycle condition. So when you are in this situation, you know that this tau p is nothing but the perturbed dynamics of your system. And what happens is that if you have an equilibrium state, a KMS state, which is also extremal in the set of all possible equilibrium state, with respect of your original time evolution, then you can build another equilibrium state for the perturbed time evolution working in this way, namely applying in this formula here. And essentially, this omega ui beta is nothing but the relative partition function of your new state relative to the original one. And then you have all the nice property you can expect. So this omega p is really an equilibrium state. So whenever you know how it is formed, your new dynamics, and if you have an equilibrium state for your original dynamics under certain condition, you can build another equilibrium state for the perturbed dynamics. But there is a little bit, and this construction was furnished, let's say, in the 70s by Araki. And there is a bit more on this. Actually, if you have your equilibrium state omega, and if a certain clustering condition holds for your perturbed dynamics, then there is a very nice feature which is called stability or return to equilibrium, and it is the following. If you consider your original equilibrium state, and if you compose it with the perturbed dynamics, and if you wait long enough, what you get at the very end is exactly this state constructed by Araki in this proposition I showed you before. And actually, this idea is very powerful because if you want to construct equilibrium state for your perturbed dynamics, what you could do is simply consider the original equilibrium state, compose it with this perturbed dynamics, and wait long enough. However, here, when we try to apply these ideas in quantum field theory, we have a problem because we proved recently that this sort of clustering condition for the case of self-interacting quantum field theory is not satisfied. And furthermore, if you try to compute these kind of limits, very often this kind of limits does not converge when your system is in the adiabatic limit, namely when the interaction Lagrangian of your system is defined everywhere in your space. Nevertheless, Fredenhagen and Lindner a few years ago showed that essentially the Araki construction can still be applied. So the construction of the direct construction of this state can really be applied also in the context of quantum field theory treated with perturbation methods. And so the idea is to use directly this theory to construct equilibrium state instead of this other property. And in the rest of this talk, I would like to briefly present the basic idea which are used in order to translate this Araki construction in the case of quantum field theory treated with perturbation methods. So here I will consider a very simple quantum field theory, namely a single scalar field with a self-interaction. And this scalar field is at the moment real, and it propagates on a Minkowski spacetime. And I will assume that this quantum field has a mass which is non-vanishing. Here I have displayed the Lagrangian density of this system. And of course, we cannot treat directly the self-interacting quantum field, and so we use perturbation theory in order to construct the observables associated with this system. So the first step is to analyze the free case, namely to set lambda to 0, forget the interaction Lagrangian, and see what happens. The theory will get satisfied a linear equation, and the starting point of our construction is the build of the star algebra of observables. Essentially, in this system, the star algebra of observables is nothing but the algebra generated by linear fields smeared with compactly supported smooth function. And the product in this algebra is formally given by this generating formula here. This is the product, and inside of this formula you have the causal propagator of the theory, which is nothing but the retarded minus advanced fundamental solution of this operator here. And the nice feature is that the algebra you get at this level is a well-defined star algebra, and for example, you can consider equilibrium states for this algebra. We will see later how to do it. And the next observation is that there is a way to extend this algebra in such a way that it contains all possible interesting interaction Lagrangian, namely all possible normal ordered local fields. These local fields are objects like this one, and essentially these are defined in such a way that if you consider the higher order functional derivative of this object with respect of the field configuration phi, you get things which are supported on the diagonal into your Mn manifold. Okay, and in order to achieve this result, you need to make an extensive use, for example, of microlocal analysis. Let's move on. And so the next step is to identify the interaction Lagrangian of your system, and the interaction Lagrangian of your system is turned into a local field after smearing it with a compactly supported smooth cutoff, this G here. And in this way, you really get an element of this extended algebra of fields I've shown you before. The next tool we need in order to build interacting field is this time-ordered exponential. And the time-ordered exponential of this interaction, smeared interaction Lagrangian B, is constructed by means of the time-ordered product, of course. And in order to construct the time-ordered product among a finite number of V of factors of type V, you need to use the theory of renormalization. For example, a method to construct this product is via the Epstein-Glaser recursive procedure. And then there is a problem in order to extend some distribution to a certain sub-manifold of your m to the power of n when you compute the time-ordered product of V to the power of n, but this can always be done. The real problem in the construction of this time-ordered exponential is the convergence of the perturbative series hidden inside of this X. And we have no clue how to control the convergence of this series. For this reason, this element here is understood as an element of as a formal power series in the coupling constant, the parameter hidden inside of this phi here. And the nice feature is that at all fixed order, the coefficient inside of this formal parameter are just nice element, well-defined element of this algebra of extended field. Once this S matrix is constructed, you can proceed very fast and consider, for example, the relative S matrix, and a functional and a simple derivative of this relative S matrix produces this known Bogoliubov map. And the Bogoliubov map is nothing but nothing but a map which takes the local fields of the interacting theory and permits to represent them as formal power series with coefficients which are elements of the algebra of free fields. And so we have a way to construct the algebra of interacting observables, which are subalgebra of this object here, which contains all possible RV of F and all possible products of this object inside of the free algebra. Okay, but now these S matrices I have introduced above, which are used to construct these interacting fields with tools of the free algebra, have a couple of nice properties which are useful in order to construct our equilibrium state. And the first property is the causal factorization property. Namely, if you have three local fields, A, B, C, and if the domain of these three local fields are constructed in such a way, the future of the support of A does not intersect the past of the support of C, then this S matrix can be factorized in this nice way. And this causal factorization property will play an important role in order to construct, for example, the interacting time evolution in terms of the free time evolution, as we will see in short. And there is another very nice property. And actually, our aim would be to consider the case where the interaction Lagrangian is mirrored with some cutoff function g which tends to 1. Namely, we would like to take the adiabatic limit. This is called adiabatic limit. And now analyzing some properties of the causal, namely using the causal factorization property, it is possible to simplify this construction. In particular, it is possible to notice that whenever you have a localized functional, localized interacting observables, if you modify the smearing function, the cutoffs of your interaction Lagrangian outside of this region, then you can always connect the Bogoliubov map applied to F supported in O, smeared with the G, with the one constructed with the smearing function G1. And actually, the nice feature is that these two objects are intertwined by a formally unitary element of your algebra, and this means that this map here can be extended to an isomorphism of algebra, namely the interacting algebra constructed with the cutoff G of elements supported in O is essentially equivalent, isomorphic to the interacting algebra constructed with the cutoff G prime. And now, using this idea, it's very easy to take the limit where G tends to 1, namely to analyze the direct limit. Whenever you are interested in observables which are localized in O, this limit can always be taken at the algebraic level. The next tool you need to use is essentially the time slice axiom. And the time slice axiom says that you can always restrict your attention to observables supported in some epsilon neighborhood of some Cauchy surface of your system. Actually, for every element supported inside of some region O, you can always find another element C, which is now supported in the neighbor of this Cauchy surface, and the two differs by a third element, W here, which has a very nice property. In particular, this W is always in the kernel of every reasonable state. So this means that when you compute expectation value of your A inside of a state omega, then these are equivalent to the computing the expectation value of your C in the same state. So this means that the information carried by this C is equivalent to the information carried by this element A. But then you can really use this idea to restrict the region where your observables are located. And in particular, you do things like this. You consider interacting observables, which are now supported in the future of this epsilon Cauchy surface, which is this orange region depicted here in this slide. And taking and then if you want to construct a state for your algebra, you just need to construct a state for this smaller algebra because of the property I've shown you before, because of this time slice axiom. So from now on, we will concentrate ourselves in constructing state for this smaller subalgebra. But then you can use this property discussed above, this causal factorization property, in order to select the cutoff function inside of your interaction Lagrangian in a simpler way. In particular, this cutoff will be divided in two parts. There will be a time cutoff and a space cutoff H. And in particular, the important thing is that this time cutoff is equal to 1 in this orange region, and it's 0 in the white region below here, and it goes smoothly from 0 to 1, from time minus 2 epsilon to time epsilon. And then the space cutoff here will be assumed to be compactly supported on the Cauchy surface. But now, if you want to take the adiabatic limit, we will assume this point of view. We will keep this time cutoff fixed, and we will just consider the limit where the space cutoff tends to 1. This is the attitude we shall consider. Okay, let's move on. And then equilibrium state for the free theory can always be constructed. We have just to say what is the time evolution of our system, and the time evolution of our system in Minkowski spacetime consists simply in the translation in time of our generator of our algebra. And actually, there is, in the case of positive mass, there is a unique equilibrium state, a unique KMS state with respect of this time evolution and inverse time times beta. And the unique quasi-free KMS state is entirely characterized by the two-point function. And here I have depicted the Fourier transform of this two-point function. And in particular, you can see the celebrated Bose factor inside of this two-point function. The next tool we need to have is to understand what's the form of the interacting time evolution. But now we have a way to construct interacting time evolution by means of this Bogoliubov map. And so the interacting time translation consists simply in the translation of the element of the local field F inside of this formula. The important point is that in the interacting time evolution, the interaction Lagrangian needs to be kept fixed. So this interacting time evolution works this way. But now, using the causal factorization property discussed above, we can really connect the interacting time evolution with the free time evolution. Actually, the free time evolution applied to the Bogoliubov map translating time F, but also the interaction Lagrangian. And you can correct essentially this translation in time of the Lagrangian with some formally unitary element, which are written in terms of their relative S matrix. And these elements here are nothing but certain unitary elements of our algebra, and they satisfy formally a relation similar to the one we have seen for the C-star dynamical system. And this means that we can also get the form of the perturbation Hamiltonian out of it. We just need to compute its derivative and compute it at this derivative at time 0. And it happens that this interaction Hamiltonian is nothing but a certain integral of our Hamiltonian density, and this Hamiltonian density at the time 0 Cauchy surface depends on space, and it is written in terms of this object here. And you see that inside of this object, the time derivative of the cutoff function key appears here. So this means that in this graph we have written above, this interaction Hamiltonian is supported only in this gray region. And so this means that if you consider the past of the support of certain observables supported in O here, the past of the support of these observables intersects the future of the support of the interaction Hamiltonian always on a compact region. This means that in this way you never have infrared problems in computing these kind of things at algebraic level. But now we have all ingredients to replicate the hierarchy construction of the state. Namely, we can analyze, we have this cocycle here, written in perturbation theory. We have our element of our interacting algebra, so we can cook up objects like this form here. And it is possible to prove that at every order in perturbation theory, the object we get can be really analytically continued for imaginary time inside of this interval here. Namely, what we have achieved, we have really we have been able to construct this interacting equilibrium state for our system. And actually, we can prove, it is possible to prove that this object defined here in this way, so in terms of formal power series, becomes really a beta KMS state for the interacting time evolution. And the other nice feature of this object here is that this state does not depend on the particular form of the cutoff function we have chosen. Furthermore, in this paper, Fredernhagen and Linder have shown that the limit where h goes to 1, let's say the adiabatic limit, can really be taken. Actually, using the decay property for large spatial separation of the free truncated endpoint function, you can really, they were able to prove that that these states really exist also in the adiabatic. And now I want simply recall a few results we have obtained in the last years, and in particular, the Fredernhagen and Linder construction works well when you have a positive mass. But now, at least in the case when your interaction Lagrangian is lambda phi to the 4, it is possible to apply the very same construction also in the case of mass equal to 0. The problem with mass equal to 0 is the following. For example, if you look directly at the truncated endpoint function of the free KMS state, you notice that they do not decay sufficiently fast in order to make this adiabatic limit well defined. Nevertheless, in this case, there is a nice feature you can exploit, and it is the following one. If you consider phi to the 4 normal order with respect of the vacuum, you notice that you can make in connection this normal ordered field with respect of the vacuum to the normal ordered field with respect of the thermal state. And you notice that when you do these things, an effective mass pop-ups into your interaction Lagrangian. And this effective mass is in the literature called thermal mass, and this means that you can use this thermal mass in order to tame you can move this thermal mass to the free part of your theory, and then this means that you can, using this trick, you can end up with the construction already discussed by Fredernhagen and Linder. The next observation is the following one, but it is a bit strange that we have constructed a state which somehow should be an equilibrium state, but it has an interaction Lagrangian which is switched on at a finite time. What you should have instead in the standard textbook is an adiabatic limit also in time. And what does it mean? It means that we would like to translate back in time our interaction Lagrangian, V and V here, and we would like to take the limit where this interaction, where this time goes to, where this minus t goes to minus infinity. This is really the limit we would like to have. However,
I think we see the wrong slide, don't we?
Oh, yes. Oh, yes,
Yeah.
That's true. I don't know what's going on here. I'm sorry. Okay. I'm sorry. I'm sorry. Thank you for saying this to me. So I hope, hopefully, you got part of what I said. And so so I said that it was possible to get this interaction. It was possible to repeat this hierarchy construction to get the equilibrium state for the interacting theory. And the state does not depend on this cutoff function, and the limit where h equals to 1 can be taken. So in the last minutes of my talk, let me summarize some result. I have already told you something about the thermal mass. Namely, it is possible to repeat this construction in the case where the mass goes to 0, at least for the interaction Lagrangian, which is lambda phi to the 4. And now what we want to do, I want to convince you that actually what we have obtained is really an equilibrium state, even if in this interaction Lagrangian, there is the interaction is switched on at finite time. Because what we should do really is to take this interaction Lagrangian and translate back in time the time where the interaction is switched on. And actually, we would like to take the limit where this t goes to, where this minus t goes to minus infinity. So this is really the limit we would like to have. But actually, because of invariance under time translation of our space-time, translating back in time this interaction Lagrangian correspond to translate in the future the observable or the field A of t. However, this translation in the future of the field A of t correspond to the application of the interaction time evolution to our interacting field. But the state omega beta v is invariant under the interacting time evolution because it is a KMS state in this case. And so this means that this object here does not really depend on time. So the limit where t goes to infinity here can easily be taken. Let me say a couple of other things. In the physical literature, very often it happens that one constructs the correlation function of these equilibrium theories using the real-time formalism. However, this real-time formalism make use of the idea of stability of equilibrium states. And I have already said to you that it is possible to prove that this clustering condition shown at the beginning for the C-star dynamical system does not work in general for a generic interaction Lagrangian. And it is and it does not work also in a theory where the interaction Lagrangian is lambda phi to the 4. We have shown here that really the correlation function obtained using this equilibrium state constructed here differs by the one obtained in the real-time formalism by a certain contribution, which may have a role in the future. And a couple of other observations. It is possible to see that this very same construction can be used in order to obtain states which show the phenomenon of Bose-Einstein condensation directly using this kind of scalar field. And finally, let me say that beyond perturbation theory, equilibrium state can be constructed in the way I have presented. For example, in the case of Sine-Gordon theory in 2 dimensions. And the nice feature is that in this case, all these perturbative series can be shown to converge, at least in certain regime. And so this means that in this way, when things converge, you really get a nice equilibrium state. Okay, so that's all I wanted to to present you. So thanks a lot for your attention.
Okay. Are there questions?
Can you say a few words about the topological questions, like what is the C star dynamical system you started out with? Does it lead to bounded Hamiltonians here or so? And how does your time-ordered exponential, you said you cannot show the convergence, and I'm wondering in what topology would you measure the convergence here? Can you say a few words about that?
Yes. So actually, here we are not using, when we really do perturbation theory, when we treat interacting quantum field theory with perturbation theory, we are actually not working with a C-star dynamical system. Our algebras are only star algebras of fields. And as said, the best thing we can do is to say that this interacting field are represented inside of our star algebras. So free fields are nothing but formal power series. So this is the only thing we can do. And this star algebra of free fields, on the other hand, have some topology that can be used in order to analyze free fields, let's say. And so that's what we obtain, which is formal power series whose coefficients are elements of a star algebra. And the same works also for this interacting state. I hope it was clear enough.
Okay. Thank you, Nicola, for the nice talk. You mentioned Bose-Einstein condensation for the charged interacting field. Can you say something about what concept of Bose-Einstein condensation you are using?
Yes, thank you for this question. I'll try to show you a slide. Hopefully I'm able to. I apologize for these inconveniences with the slides. And so when you have a charged scalar field, then you can try to build a Bose-Einstein condensate also for this kind of system. And so the concept of condensation, or the notion of condensation we are using is the following. We assume that a state exhibits Bose-Einstein condensation if there is a non-vanishing one-point function into our system. And what happens when you have a non-vanishing one-point function, a state exhibiting a non-vanishing one-point function, is that the natural U1 symmetry present in this system is actually spontaneously broken inside by this state. And actually, this symmetry, this U1 symmetry, is generated by a natural current, and in particular, the charge density associated to this natural current replace what is usually used in the case of particle physics as it's a replacement of the particle density in the case of non-relativistic theory. And somehow, if you measure the charge density inside of the states which shows this spontaneous breakdown of the U1 symmetry, you can really distinguish between different phases. And actually, another observation is that if you have this kind of state, and if you try to compute the correlation function of, for example, the charge density for large spatial separation, you get that because of the non-vanishing one-point function, this decaying that large spatial separation is not mild. You don't have a decay, actually, in this. So this is the notion of Bose-Einstein condensate we are using.
Okay, thank you.
Okay, maybe just I have one quick question. Is there any chance of extending these analogies to gauge theories as well?
Yes, I think it should be possible to extend this theory also to gauge theories. But of course, there is some work that needs to be done in that case. At least the part regarding the construction of interacting field works more or less the same way. The difficult part is to understand how to implement the gauge theory into the system.
Okay, so if there are no more questions, we can thank Nicola again.